Another example of mixing application of differential equations. So a tank contains 100 gallons of brine in which 30 pounds of salt are dissolved. So that's my initial condition when time is 0, y is 30, y is the amount of salt at any given time t. Another brine containing 2 pounds per gallon is poured into the tank at a rate of 8 gallons per minute. Mixture is thoroughly mixed. Mixture flows out of the tank at a rate of 6 gallons per minute. How much salt is in the tank after 30 minutes? Okay, so let's start by thinking yt, let yt be the amount of salt at any given time t. At any given time t, yt is the amount of salt at any given time t. So dy dt would be equal to rate in times concentration in minus rate out times concentration out. Now, rate in, we know the rate in, that is 2 pounds per gallon times 8 gallons per minute. 2 pounds per gallon times 2 pounds per gallon times 8 gallons per minute. That's the rate at which we're putting things in. And getting out, we know the rate at which it's getting out. The rate is 6 gallons per minute. But we don't know the concentration when it's leaving the tank. So concentration would be amount of salt, which we're saying at any given time t, amount of salt is y divided by the volume. Now be careful over here with the volume because we're putting in the mixture at 8 gallon per minute. We're taking it out at 6 gallon per minute. So each minute we are adding 2 gallons of mixture, 2 gallons of liquid into the tank. So the volume is increasing. We started with the volume 100 gallon, but with each minute we are adding 2 gallons of water because the rate in and rate out are different. We're putting more water in than we are taking out. So with each minute we are adding 2 gallons. If after 1 minute it would be 100 plus 8 minus 6, which is 102 gallons in there. After 2 minutes, it would be 100 plus 8 minus 6 minus 6. That would be 104, right? So each minute we are adding 2 gallons. And we don't know how much time has passed, so we're just calling it 2t. All right, so dy dt, let's clean up this equation. That would be 16, gallon and gallon is gone, 16 pounds per minute, minus, that would be 6y over 100 plus 2t. Okay. Now see, take a look at it carefully. If it's a separable differential equation, when your rate in and rate out are different, they're not going to be separable differential equations. This would be a first order linear differential equation. When rate in and rate out are same, that's when we will have the separable differential equations. But if the two rates are different, it would be first order linear. So first order linear is p of x, y prime plus p of x times y is equal to q of x. That's the way to express the first order linear equation. I'm going to put it in the nice shape and form. Dy dt plus 6 over 100 plus 2t times y is equal to 16. And now it is in the first order linear form. I'm going to go ahead and find the integrating factor. At this point, if you want to make your life easier, you can go ahead and cancel the common factor 2 between these. 6 over 100 plus 2t, you can cancel the common factor if you want to make your life easier. Let's go ahead and think about the integrating factor now. I'm going to write it on the next page, that way I have more space. Dy dt is equal to 16 minus not dy minus let's see, plus 6 over 100 plus 2t plus 6 over 100 plus 2t times y is equal to 16. That's my differential equation. So integrating factor is going to be e raised to the power p of x dx, which is going to be e raised to the power 6 over 100 plus 2t dt. Now we need to have the derivative of denominator sitting in the numerator. In order for me to use a natural log, derivative of denominator would be 2. So I'm going to separate that 6 into 3 and 2. Now I can say this is going to be e to the power 3 natural log of 100 plus 2t. 3 natural log of e raised to the power 100 plus 2t. E raised to the power 3 natural log of 100 plus 2t. That's what turns out to be my integrating factor, and I can express it slightly differently. I can say this is e raised to the power natural log of 100 plus 2t raised to the third power. Time is never 0, so I'm not going to worry about the absolute value sign here. E and natural log, when we raise e to natural log of something, they're using the rules of exponential functions. This is going to be 100 plus 2t to the third power. 100 plus 2t to the third power. That is my integrating factor. So now I'm going to multiply both sides of this equation with the integrating factor. So I have dy dt times 100 plus 2t to the third power plus 6 over 100 plus 2t times y times 100 plus 2t to the third power equals 16 times 100 plus 2t to the third power. We have seen earlier when we solved the first order linear equation that your left hand side is the product rule of y times the integrating factor, 100 plus 2t to the third power. And the right hand side we're going to integrate here. That would be 16. We actually integrated both sides, but the left hand side is derivative of a product rule of these two things. So derivative and integration are opposite of each other. They cancel each other. We're left with 1600 plus 2t to the third power dt. Okay, so this integral, we can do the u substitution here, and this integral is going to be, we will raise it to the power 4. So y times 100 plus 2t to the third power is equal to 16 times 100 plus 2t to the fourth power divided by 4 and also multiplied by 2 derivative of inside piece plus a c. Okay, only thing we need to do is now clean up a little. Looks like we are almost done with solving. So this is y times 100 equal to 16, and we have 4 times 2, and that's going to give me 8. That would be a 2. 2 times 100 plus 2t to the fourth power plus a c. That's what we are left with now. And now we can go ahead and divide both sides with 100 plus 2t raised to the third power to isolate the y. 2, that would be 100 plus 2t only plus c times 100 plus 2t raised to the power negative 3. Okay, that looks like that is going to be my solution. I can go ahead and distribute. I can write it slightly differently if I want to. 200 plus 4t plus c divided by 100 plus 2t to the third power. So both ways you can express your solution. Now we are given initial condition. Initial condition was, we were told that when we started, how much there were 30 pounds of salt when the time was 0. Initial condition is y is 30 when t is 0. Let's use it to find the c. So y is 30 when t is 0. That is going to become 0 plus c over 100 to the third power. So 30 is equal to 200 plus c over, it's going to be, all right, so to solve it, 30 minus 200, let's see what does c come out to be. 130 minus 200, c is going to be 30 minus 200 times 100 to the third power, that's times 100 to the third power, which is negative 170 100 to the third power. Negative 170 100 to the third power. So now we have our constant c, and we can find at any time t. So at time t is equal to whatever time we were looking for. We were being asked to find out, find the amount. Can't find the 2 gallon. Nope. What's this problem? 100 gallon tank. Where's this problem? So a tank contains 100 gallons of brine. this was a problem. Mixture is thoroughly mixed. What we were looking for, we had to find the amount of salt after 30 minutes. So how much salt do we have after 30 minutes? So at 30 times t is equal to 30, we're gonna plug 30 for our y is equal to 200 plus 4 times 30 plus negative 170 times 100 to the third power divided by 100 plus 2 times 30 raised to the third power. And what's going to be the units in this case? Look at your problem and see what units you started with. We started with, it would be pounds. So that's going to be the amount of salt. It would be in pounds. And I'm not going to solve it. You go ahead and solve it. Let me see if I plug into a calculator. 200 plus 120 plus fraction negative 170 times 100 to the third power divided by 100 plus parentheses around plus 60, which is 160 to the third power. So 160 raised to the third power. That turns out to be 278.49. So y is approximately 278.49 or 0.50. We can round it, 278.5 pounds. Okay. That's it for this video. We looked at an example of mixing application of differential equation when rate in and rate out were different.